Okay, we are going to start with Brian Hoskins from UCB, and he's going to talk about modulation of forming voltage in reactively sputtering titania and resistive switches. So you're going to have 20 minutes. And, okay.
Thank you. I'm Brian Hoskins from the University of California. Thank you. All right. So I'm Brian Hoskins from the University of California, Santa Barbara in the Department of Material Science and Engineering. And my advisor is Professor Dmitry Strokov in the Department of Electrical and Computer Engineering. And this project is one that I've been working on for the last 2-3 months or so. And it's very much a work in progress. And I appreciate your input on what's going on so far. There we go. So I think we've all seen these kind of plots before a million times or so about how you have basically a filament that is of some reduced TiO2, which can its shape can be modulated by the application of positive and negative voltages away from some interface which controls the conductance of the entire resistive stack. And one of my favorite ways to actually observe the effect of reduction in these films for all the spectroscopy and all the CAFMs and all the electronic measurements, you can actually kind of see the bubbles, which I really very much enjoy. And so this was done. This was done at HP, and this was done at a group at National Chongqing University in Taiwan. I was actually in Taiwan when this actually was published, and though they exhibit the bubbling occurring at 4 and 3 volts, they actually undergo their irreversible electroforming process at somewhat higher voltages. So this is pretty cool. And if you actually just think about the thermodynamics and just calculate from the Gibbs free energy change of the oxides, you actually calculate a significantly lower voltage of equilibrium between TiO2 and TiO407, just from like classical thermodynamics of electrolytic cells. And so kind of a simple point is this data comes from measured data, not calculated, mostly from the 50s, 60s, 70s, and 80s on titanium, and also from NIST, that you can kind of estimate what you would thermodynamically think the forming voltage might be. And the reduction happens at much higher voltages than predicted, and so we think this might be due to Joule heating. And so here are just 2 examples. And in our group, we don't really have any measurable leakage current at a volt, and our forming voltage is about 7 volts. At HP, the groove films of about 4 nanometers of thickness. So you can imagine you have direct electrode-to-electrode tunneling, so you have significantly higher current densities. And also at PGI, which in a group led by Rainer Weiser, they also exhibit this kind of change in the stack conductivity just by changing the electrodes. And I think if you go through the literature, you'll in fact see some fairly consistent trends that increasing the voltage current density through your film will produce more watt per volt and give you a lower forming voltage. And so we want to do the same thing, but by changing the composition with reactive sputtering to change the resistivity of our stack. And so the problem with doing reactive sputtering is that you have positive feedbacks, because as you oxidize the titanium target, your sputter rate falls, and so the partial pressure of oxygen will increase as the amount of free titanium introduced into the system is reduced. And so in general, you are driven towards either depositing either TiO2 or titania. And so in general, there are forbidden regions of values of TiO2 minus X which you're unable to access in the typical sputtering process. And so from the Berg model, which is basically just a detailed ballast of all the gas in and out, you can more or less determine what are the conditions under which you could expect to have a hysteresis-free control of your reactive sputtering process. And what you basically do is you consider the pumping rate due to your pump, due to your deposition region, and also due to the target. And you consider the effect of the change in pump rate in your target due to the oxidation state of the target. And so the implication of the Berg model is that hysteresis is lifted by having a small target and a large pump. So effectively, as your pump becomes very, very large and your target becomes very, very small, essentially your background partial pressure of oxygen becomes explicitly a function of only the flow rate and the pump rate. And so you remove this hysteresis effect. And so I did a maximization of the pump rate this is kind of my O2 flow condition. The order of magnitude for the partial pressure of oxygen is on the order of 10 to 80 microtorr. I do my deposition parameters 90 SCCM of argon, background pressure of 1 millitorr, 125 watts of DC power, deposited at room temperature with a 2-inch diameter target in a very large turbomolecular pump. And so the outcome is I have hysteresis-free growth on my titania deposition. And so I measured these ones with ellipsometry and AFM, not ellipsometry, but with AFM and profilometry, because the ellipsometry models failed to fit them. And over here in this, I don't have to go back. How do I go? I don't know what button to press. Sorry. All right. So in this region, you essentially have stoichiometric titania, ellipsometry models fit. And so the main implication of having basically continuous control over your growth rate is that you also have continuous control over your stoichiometry. And so basically the outcome is that you have the resistivity control from 0 to 5 SCCM. This was measured via a 4-point probe technique. And so now that I am fairly confident that I have more or less continuous control over my oxygen stoichiometry in my films, I proceed to build stacks of platinum, TiO2 platinum, with 100 nanometers of titanium dioxide. And my objective is to make these 100 nanometers of titanium dioxide have the same forming voltage as you would have in a 4 nanometer thick region of titanium dioxide between platinum electrodes. And so I have pads from 50 by 50 to 25 by 2500 micrometers. I conduct AFM calibrations immediately prior to growth, and that's primarily because I do my platinum deposition in situ at room temperature. And I checked for edge effects because I had to do liftoff, and basically you have rabbit ears, and you have pull away of the top electrode from the film. So edge effects shouldn't be too serious a concern, but they might be there. And so this is a result for O2 equal to 6.875 flow rate, and the forming voltage is at approximately negative between 8 and 9 volts. And so for a 100 nanometer stack, you might expect something between 10 and 20 volts for your forming process. And I have here a few other devices which exhibit this kind of order of magnitude for the forming voltage. You can switch these devices. The on-off ratio isn't particularly high. And here are several other devices with that particular relationship. If you go too far, you essentially can't form your device anymore. You don't have access to the forming property of the film. And if you go to O2 equal to 6.25, you can actually reduce the forming voltage to, in this case, around negative 2.7 volts, and here around 2.1 volts. And so I can tell you from Van der Pol measurements that the film resistivity of this particular film is about half an ohm meter. So when I set out to do this experiment, you have 15 or 20 orders of magnitude between titanium and TiO2 in terms of resistivity, and I had no idea under which regime you'd actually be able to locate something measurable. And so 0 to 10 ohm meter you can actually measure in conventional Van der Waal configuration. And so here's some of the switching for the negative forming direction and the positive forming. The on-off ratio isn't particularly great, since this, which I think is to be expected since you've eventually converted your insulator into just a very, very, very leaky insulator. But the key point remains that you can modulate the forming voltage through this particular mechanism, and you can potentially use it to get other new switching properties. And so I actually observed some other more interesting behavior in the films besides this kind of reduction in the forming voltage. But for some of the devices, actually at the same flow rate, which I'll discuss why that is in a moment, you have this interesting relaxation from the initial state into a new state. And I'm not entirely sure what this effect is.
Just ask before, so we don't forget, these kinks, does that depend on the rate how you sweep your voltage or not?
I'm not sure. I don't know. I'm sorry. So the immediate post state to this first initial relaxation is about 2 orders of magnitude in lower conductivity, and it also exhibits a small amount of hysteresis between -1 and 1 volt. Now, if you try to do a current-controlled sweep to higher voltage, you actually get something that appears to be kind of like a unipolar transition. And so this is interesting, and you can actually turn it off by just sweeping to positive voltage, and that turn-off is around 0.7 volts. So that's kind of cool. And now if you're extra clever, and you do a voltage-controlled sweep, you can actually put it into a bipolar transition state because you turn it on and then you immediately start to turn it off. At least that's what I think. And you have this kind of bipolar switching in this nice, fairly vertical climb. This is a kind of a better device, and as you can see, you have actually better on-off ratio than in the previous devices. And the switching is fairly interesting. And you can do this for a couple other devices. You can do it for different polarities. And as you can see from both of these forming directions, you have both, but you can still get kind of the same polarity. So I'm not entirely sure what this initial state represents, but I think kind of a better measure of what's going on in the film is the fact that after this relaxation step, your baseline film from which you proceed to do resistive switching is in general a very, very conductive film. And so that's why you see all this behavior at relatively low voltages. So I think probably that relaxation might be due to the fact that you have some strange stoichiometry in the film, and as you increase the temperature, there might be some changes in the ionic coordination or something like that. But that's something that I'm definitely interested in investigating. But anyway, the real problem is that there's actually incredibly low reproducibility. The reason both of those two films of very different characteristics were grown at around the same flow rate, and the reason is if you try to do measurements of the same flow rate and try to get the same resistive switching property, you'll find that there's actually, from day to day, you can get swings in the resistivity for about 3 orders of magnitude. And so the reason for this is that you have fairly large derivatives in your O2 SEM, in the region of interest. This is around 6.25, and it's actually the region where you have more or less the least amount of stability in your growth. And so a typical mass flow controller only has 1 to 10% accuracy of the max flow through the film. So in general, you'd expect this entire region to be, as you go from weeks and days on, as your target degrades, and as your mass flow controller just does interesting things, that these regions would be equivalent. And so in order to solve this problem, you essentially need to change your process parameters completely and make this region, in terms of O2 flow, as flat as possible. And there are 2 ways you can do that. So from the Berg model, you know that from the pump rates, you can bend the film. You can bend this curve, but you also know that if you just increase your deposition rate, you can stretch it, and so hopefully that way flatten it so you can extend this curve in this direction. But also, if you were to do a deposition to, say, a TIO, a TI205 target, you would essentially eliminate these degrees of freedom as well. And so ideally, you could have within your entire domain enclose your entire composition range of interest. And that's actually what I'm planning to do next. And so in summary, I demonstrated control of titania stoichiometry in films by implementing recommendations of the Berg model. And I realized lower forming voltage devices, and I also yielded a lower on-off ratio in general. And I observed interesting on-state, initial state in certain highly reduced films. And the primary obstacle to further study is the process instability associated with target lifetime and instabilities in the mass flow controller accuracy. So thanks a lot. This is my group. Please ask me any questions.
Thank you for this nice talk.
From our experience and also the experience from other group, from the literature, it's reported that the crystallinity plays a key role for the forming voltage. So not only the oxygen vacancy content itself. Could you comment on the change of the crystallinity of your thin films with the varying deposition conditions?
In general, I deposited everything at room temperature.
Okay.
And so, in general, if you do your depositions below 300 degrees C, you should have amorphous films of titanium dioxide, particularly since it's a tetrahedrally coordinated solid. So I didn't do XRD on the films or anything like that, if that's what you're asking, as a function of the change in flow rate. But I do know from that if you go contact companies that do sputtering, they will actually market essentially amorphous films deposited of titanium dioxide at more or less arbitrary stoichiometry, and particularly for use as an electrode material. So I believe that, in general, the films should be completely amorphous, and whether or not that changes, though, during the forming process, I think is another question altogether. But I don't have any measurements to claim otherwise.
But that would mean that the surface is completely flat. So as soon as you start to crystallize, you will see these islands on the AFM pictures. So this is always the first hint on that you start to crystallize if your surface becomes more rough. So that you don't have to do XRD, you always get some sign from the surface.
All right, I'll look into that.
My question is on the size of the samples and reproducibility. What's your experience on that?
Like the size of my wafers, or?
No, the size of the device, the lateral size of the device.
Oh, they're huge. They're 50 by 50 to 250 micrometers is the ones that I did the most measurements on. And in general, once you figure out an algorithm to how to do it, and that takes a long time for each in particular, because each time it's a different film, and each time you have to figure out more or less the voltage compliance associated with the forming. So when you're trying to figure out how to form the devices, you burn almost all of them. But once you figure out what you're doing, you can more or less get, I'd say, most of them to switch. The only problem being is that some of them will be significantly better than others. So in terms of quality of every device, that will have low reproducibility.
Basically, what I learned from your talk is that if you increase the size of your pump, you can have full control of the stoichiometry, right?
Yes.
For reactive sputtering. Do you see other ways of controlling stoichiometry besides in reactive sputtering, besides just increasing the pump size? I mean, from that study of Berg?
So actually, in the previous study, I forget the guy's name, but I can go back. This guy, Spool. So you in general in this region you have kind of an S-type hysteresis, which you are free to explore if you also have positive feedback on your mass flow rate controller. So there are for market at significant capital expense. You basically can just buy a residual gas analyzer, attach it to your system, and then have active feedback. And so in general, you still want to use the Berg model to stabilize it, because you will still kind of have oscillations. That's what you can see in the literature. But if you combine all these elements together, you'll have the maximum amount. So if you have if you don't have an S-shaped curve and you have this kind of active feedback, you'd probably be in like the best shape for reproducibility.